Hi everyone, this is Professor Bergasser and this video is on coordinate systems. These are the maps of physical quantities in space, and they're very useful as a framework for solving various physics problems. So in this video we're going to talk a little bit about the purpose of coordinate systems, introduce coordinate systems in 1 dimensions, 2 dimensions, and 3 dimensions, and then give a few best practices on how you choose a coordinate system that best suits your problem. So again, these coordinate systems are really maps of how we measure physical quantities distributed across space. And you can have two different kinds of coordinate systems. There are scalar maps, which map scalar quantities through space. And great examples of these kind of coordinate systems include just regular maps. Or you could have maps of topography or altitude. Or you could have something like a heat map or temperature map like you see on the weather. All of these maps map a scalar quantity as it's distributed around space. Another type of map would be a vector map to cover our other type of physical quantity. And a great example of this is a map of wind speed, which shows both the magnitude of the wind and its direction. So all of these maps have a similar quality. They map physical quantities in space. Sometimes you'll see that these are referred to not as maps, but as fields. That word's going to come into common play when you get to 1B or 2B in electromagnetism. But they're basically describing the same thing, where physical quantities are distributed around in space. Now, all of these different maps or coordinate systems or fields have similar properties or similar characteristics that define them. So when you're making your coordinate system, you want to keep these characteristics in mind. First is they all have an origin. Right? They all have a 0 point from which you measure the relative distances or positions of whatever physical quantities you're looking at. Another thing is that they all have orthogonal axes defined by their unit vectors. All right, so if you remember from our vector video, we talked about how vectors have unit vectors that determine just the direction in which these vectors point. So coordinate systems have unit vectors that define them, and they define them on orthogonal directions, which means those directions come into right angles. And so if you have, for example, a Cartesian coordinate system, which we'll see in a moment, the x and y axes, which are very commonly seen in different coordinate systems, are always 90 degrees with respect to each other. They map completely different directions in space. This actually limits the sort of dimensionality of our coordinate systems. We're in a three-dimensional space world, so at most we can have three coordinates define our coordinate system. Another common property of coordinate systems is that they have a scale, right? And that's both number and unit, all right? Most often these scales are mapping spatial directions, but you could also get in some cases where the coordinate systems are actually mapped in velocity space, in which case those scales are measured in velocity units. We'll mostly be sticking with coordinate systems that are based on position only, spatial coordinates only, but make sure you keep in mind that those coordinate systems have to have units associated with them because they are measuring a physical quantity, which is the position or direction or distance in a coordinate system. And then the last property is that the physics is independent of the coordinate system. Okay, now what do I mean by that? Well, if you think about, for example, a topographic map, the mountain will exist whether or not you have a topographic map or whether you measure the topographic map in meters or miles or yards or whatever unit you want to use. And so when we talk about the actual problem, that problem exists in space. It's something that you can solve. The coordinate system is something that we decide to map onto that problem in order to solve it. And so most of the process of choosing coordinate systems is choosing a coordinate system that makes the problem easiest to solve. But independent of whatever coordinate system you choose, you should always come up with the same answer in terms of, for example, the acceleration or the velocity or position of the objects that you're interested in. So let's start with our first dimension coordinate system, which is our easiest coordinate system because we're only talking about one direction. And that turns out to be the number line. There's really not a lot of choice in what kind of coordinate system to use in this case. And so this is an example of a number line which I've drawn in a vertical direction. And notice a few things about this. One, we've specified the origin of the number line. It has a clear direction, which is specified by the arrow here. That sort of represents my unit vector for direction of which way the coordinate system is defined. I've made sure to label the coordinate system both in its units, in its quantities and its units, which is in this case meters. And of course, again, any of the physics I do is going to be independent of this choice of coordinate line. I'll show you an example in just a little bit. If I just change this around, we should still get the same answer. Now, so usually the 1D coordinate line system is very easy to work with, but a common misconception is whether or not there are vectors defined on the 1D line, and in fact there is. So let me make sure that that's clear, that vectors are defined on the 1D coordinate system. All right, so as an example, let's imagine that I have two displacement vectors. So I'm moving an object with one displacement followed by a second displacement. So I'll write down that first displacement. Let's say I'm going to move it up by 2 meters. Well, that's my number, my unit, and then I have to have a direction, which I could write down up if I want. Based on this coordinate system, that's in the same direction as my y-coordinate. And so I could write this in the coordinates I'm working with as 2 meters in the y-hat direction, the positive y-hat direction. Now let's say I have a second displacement, and that's going to be 1 meter in the down direction. All right. So just like all my vector quantities, I have a magnitude, a unit, and a direction. In this coordinate system now, down is actually pointing in the opposite direction as my y-hat coordinate. And so this is now actually minus 1 meter in the y-hat direction. So notice the minus sign came in here because I'm pointing this vector in the opposite direction in which my coordinate system is defined. And so minus signs are often kind of confused in these systems. Vectors always have a positive quantity, but if the direction of the quantity is in the opposite direction of the coordinate, you have to have a minus sign in front of there. So let's actually sketch this out. So if I start at the origin and I move by my first displacement here, and then followed by my second displacement, I'll just go from head to tail. So there's my second displacement. And then the sum total of these two vectors is, again, just following tail to head, and the net vector is right here, r1 plus r2. Okay? So let's actually write this down in our usual vector notation. So r1 plus r2, all right? Again, I can write this in units of the vectors that I have here, 2 meters up plus 1 meters down. But remember, when we're adding these vectors, we have to make sure that we're adding up the components along each of the directions. In this case, we only got one direction to worry about, and that direction is the y-hat axis. So I'm really just adding up these two columns, 2 meters in the y-hat direction plus minus 1 meter in the y-hat direction. And that sum is 1 meter in the y-hat direction. And we can check that, indeed, we have our net vector going up in the positive direction, our number axis, in a unit of 1 meters. So we can still consider vectors on these one-dimensional number lines, and it just decides which way the sign is flipped. All right? If you're going along the direction that you define positive in your coordinate system, then you have a positive displacement or a positive velocity. If you're going in the opposite direction, you just have to make sure you have a minus sign. So moving up in dimension, now let's go to 2 dimensions, and we'll see we actually have 2 different coordinate systems that we commonly use in physics in this sort of dimensionality. The most common one is the Cartesian or rectangular coordinate system. This is probably the one you're most familiar with in terms of mapping out space in 2 orthogonal directions, x and y is commonly used. And orthogonal, again, because these are at right angles, and so you're actually spanning the entire 2-dimensional space with just these 2 vectors. Now again, looking at my coordinate system, I've got to make sure I've got all of the elements that I need to define for it. We've got an origin for our coordinate system. We've got our direction specified by the arrows, our unit vectors pointing in the x and y direction. We have our scale, which is in meters, and the tick marks are marking off individual units of meters. And as we will see, we can also do this problem independent of the coordinate system. This is just one that we choose if it turns out to be very handy. So just an example of how we then write down some vectors. Let me just draw in a vector here, a displacement vector going from the origin to a point up here. We'll call that vector r. And the way that we write this vector depends on what kind of problem we're doing. Again, we have multiple ways of sort of writing down these vectors based on their coordinates or based graphically like this. And so because there's two dimensions, we actually have to have two numbers to specify it. So I can specify this coordinate by its x and y extensions. All right. In this case, we can actually look right at the map and see that this coordinate is moving in 4 units in the x direction and 3 units in the y direction. And so this is 3, oops, let's erase that. Okay, so that is a 4, 3, and in meters vector. All right. Another way we can write this is in our unit vector notation. And so I could write 4 meters in the x hat direction plus 3 meters in the y hat direction. And of course I can also just write down the magnitude of the vector and its direction. And in this case, we'd actually have to compute what the length of this vector is, but that's actually pretty easy because it's just this is a right triangle, right? The coordinates that I've written down here. All right, this maps onto this x-axis, this maps onto the y-axis. This is a right triangle, so we can just use Pythagorean theorem to show that it's going to be 4 squared plus 3 squared. Square root of that makes a triangle that's the length of 5 on the hypotenuse. And so this is also 5 meters in the sort of this direction. Or if we want to be more specific, we can specify what this angle here is. All right. That angle is simply the inverse tangent of these sides. Remember, tangent, TOA, opposite over adjacent. So we can calculate the angle as 3 over 4, and the inverse tangent of that turns out to be 37 degrees. So we can specify this a little more specifically by saying this is 5 meters, 37 degrees counterclockwise from the x-axis. Now we can close the loop on this and see how would we write this vector along its coordinates if all we're given is the length of the vector, the magnitude of the vector, and the angle with respect to this x-axis. Well, again, let's look at this triangle. We can see that the projection of this vector along the x-axis, this is the adjacent side to this angle. And remember from our SOHCAHTOA rule that adjacent over hypotenuse gives us the cosine. And so I can write down x as the length of the vector r, all right, that's the magnitude of our vector, times the cosine of the angle. Okay, and we know that this is 5 meters as the length of the vector, and cosine of 37 degrees, which we would find out is equal to 4 meters. And similarly, we can write down the y-coordinate. The y projection is on the opposite side of the angle. That's the sine function, r sine theta, 5 meters sine 37 degrees. And we would find out that that's equal to 3 meters. Okay, so you can go back and forth between these two different parts of the vector, either just the magnitude and its direction or the coordinates in this coordinate system by just some careful use of trigonometry. But that's the great thing about this rectangular coordinate system. It's very easy to go back and forth between these. Now I'll just say I've drawn this coordinate system in a sort of nice vertical horizontal orientation, but that's not the only orientation you need to have for a rectangular coordinate system. Later on we're going to see problems that, for example, where we're looking at a wedge, right, that has some kind of inclined plane, and we might want to measure the motion of a block sliding down this plane. Now in this case, gravity may be pointing down, so that might be a convenient coordinate system to have this coordinates going horizontally and vertically. But if we're just interested in the motion along the plane, we might choose to draw a coordinate system that's aligned with the wedge. So you can imagine maybe using a coordinate system where the x-axis is parallel to the wedge and the y-axis is perpendicular to it. Right. This is still a rectangular coordinate system, it's just rotated around. So make sure you play around with these coordinate systems a little bit to make sure you pick the one that's best for your problem. Now in general, the rectangular coordinate system is the best one for 2D motion, but there are some kinds of motion where it's actually useful to use another coordinate system called polar coordinates. And this is particularly useful for motion that involves some kind of circular component. So orbits or spiral motion are often well done with polar coordinates instead of rectangular coordinates. And so many of you may have seen this kind of radar map coordinate system before. What this is mapping is two directions. One is the radial distance away from our origin, so we have specified an origin, and the sort of angular direction around the circle. So if I draw a vector in here, for example, that one right there, I can specify that by two coordinates, one of which is the radial coordinates, and the other, which I'm going to call phi, which is the angular or rotation coordinate. We'll just call it the angular coordinate. All right. Now, the angular coordinate, you have to make sure you specify it relative to something else. So kind of ironically, what's often done is you choose the x-axis again. So just a reminder that if this was our x-axis from before, we'll put our little hat there, and this is our y-axis from before. It's often common to draw the angle for this vector relative to that x-axis. So here is my angle, and we'll call it phi. Okay. So both of these two coordinates are used to specify this vector, and just like x and y, you need to have two coordinates because you have a two-dimensional coordinate system. Now, this coordinate's a little funny because, in fact, if I write down, so if this is my point that I'm interested in here, and I write down the actual vector in polar coordinates, that vector r is just equal to the radial coordinate alone. So why do we need that angular coordinate? Well, as this thing may be rotating around, the direction of that r hat vector pointing from the origin out to the point is itself changing. And so you actually need to specify this angular coordinate to tell you which way r hat is pointed. This is kind of a funny unit vector. And so if we break this down into coordinates, all right, let me actually draw my unit vectors in here. All right, this is the direction specifying r hat. And if I'm assuming this object is rotating counterclockwise, so around this direction from the x-axis, then this is specifying the direction of rotation, which I'm going to call phi hat. All right, so I can write down these coordinates in terms of these unit vectors. So again, that's r hat, but I can also write the unit vector r hat in terms of my x and y rectangular coordinate system. And so that's actually not too hard to do. All right, that's just equal to the, and actually make sure we're clear here, we're writing down the coordinates for r hats. All right, so that's in terms of x hat, and that's x hat times cosine phi plus y hat times sine phi. And the phi hat coordinate is equal to minus x hat sine phi plus y hat cosine phi. Now, how was I able to write that down so quickly? Well, we can do our example of looking at the sort of extreme cases for cosine and sine. When phi is equal to 0, the r hat vector is pointed entirely along the x hat direction. And so when phi equals 0, in this case, cosine phi is equal to 1, and sine phi is equal to 0. So you have an r hat vector that points entirely in the x hat direction. For the phi hat coordinate, all right, that when phi is equal to 0 is actually pointing straight up, so pointing entirely in the positive y direction. As it rotates around to 90 degrees, it's pointing in the negative x hat direction. So let's stick in 90 degrees. when sine of 90, you have sine of 90, that's equal to 1, so I should have something that points in minus x hat direction. When I have 90 degrees of cosine, that's 0, so there's nothing in the y hat direction. So using these extreme examples allow you to sort of double check the coordinates or way that these coordinates are mapped onto each other. And immediately can see why we might want to use a polar coordinate system for rotating motion. Keeping track of all these angles might be kind of a difficult thing to do, whereas if you just have a simple r and phi coordinates, it's actually a little easier to keep track of that kind of circular motion. Now this, just to give it some examples of the kind of motion you might see, it will depend a little bit on how r hat, or how r and phi are changing. So if r is constant and phi is changing, then you've got the case where you're actually following along one of these lines at constant r. So this is circular motion. That's a circle. All right. If you have the case where r is changing and phi is constant, all right, that's the case where you're staying on one of these angular lines, but you're moving in or out in terms of radial coordinate. That's just linear motion. And in fact, often that motion is probably better be described with a rectangular coordinate system. You can also have the case where r is changing and phi is changing. And that's probably the most interesting case, because you might, maybe if you're increasing r and increasing phi at the same time, you're wrapping yourself out. This is spiral motion. And there are some cases in physics where we look at spiral motion. Now that we've seen two different ways of representing two-dimensional coordinate systems, now let's talk a little bit about three-dimensional coordinate systems. And you'll be not surprised to know that there's actually three different ways of representing those. The first most common way is just an extension of our rectangular coordinate system into the third dimension. And so in addition to the x and y axes, we're going to include a third axis that points in the orthogonal direction from these normal axes, x and y, that we've used before. All right, so I'll draw those in. And again, it's important to specify the directions, some kind of scale, and the origin of our coordinate system. Now, this coordinate system is defined in a right-hand manner that follows the right-hand rule, the same rule that we talked about when we talked about vectors and cross products. The right-hand rule in this case tells us that when we have our x-coordinate and we cross it into our y-coordinate, that gives us our z-coordinate. So this is a right-handed coordinate system. Sometimes you'll see them flipped around in some different way, but this is the most correct way of drawing these sort of three coordinates following the right-hand rule. Now, if we have a vector on this coordinate system, so drawing from the origin up to some point in our three-dimensional coordinates, these coordinates are written, the vector again is written down in the number of coordinates that are displayed, which is 3 dimensions. And those are just the projections of this vector along these axes. And so I can write my vector here, my position vector, as a combination of 3 numbers, or as a combination of 3 magnitudes plus the unit vectors. All right? So again, because we have 3 dimensions, we have to specify 3 different coordinates, and we're doing this in the x, y, z coordinate system. A second coordinate system that's commonly used is the spherical coordinate system. This is kind of an extension of our polar coordinate system into 3 dimensions. And it's easy to sort of show this by first sketching in our x, y, z axis, and then just indicating our surface of constant radius, right? In this case, if I have a vector pointed in this coordinate system to this radius, r, that coordinate, or that vector, is specified by 3 coordinates. In this case, they are the radius, our phi angle, which is the direction around the xy plane, and another angle, which is often written as theta, and that's the angle with respect to the z-axis. And so if I were to draw these on this diagram here, again, if we specify this to be our reference, x hat, y hat, z hat, right? If I project this down onto our plane, this is kind of the angle with respect to the x-axis, that's our phi. And this is the angle here, theta, with respect to the z-axis. So again, just like our rectangular coordinate system, we have to specify three different numbers: the radius, the angle along the xy plane as we project down onto that plane, and the angle with respect to the z-axis. Right? All three of those are needed. Now, the third coordinate system that's commonly used is called the cylindrical coordinate system. And this coordinate system is a combination of the z from the rectangular coordinate system and our polar coordinates. It's kind of literally a projection of polar coordinates straight up vertically. So if I, again, draw for reference my x, y, z coordinates, in this case, our r vector here is going to be a combination of what the projection is along the xy plane, so again specified by an angle phi, but all we then care about on the z-axis is where it is up here on the z-axis. Okay, so in fact that axis is still in there. And so we would specify this coordinate by, again, three numbers, r, phi, and z. Right? So this cylindrical coordinate system is very commonly used for gyroscopic motion, or looking at, for example, the motion of the helicopter blades of a helicopter, or even mapping along your arm, which is mostly a straight axis along here but has a circular component as you go around. The spherical coordinate system is very useful for looking at any kind of force that is centrally located, like the gravitational force, as we'll see later on, or electrostatic force. Or if you want to see how things move as they're distributed evenly out into space, spherical is a good way to go for that. But of course, for most of our applications, we'll probably be looking at rectangular coordinate systems because they provide sort of the easiest framework to work with. So we've just looked at all different kinds of coordinate systems, so I want to summarize sort of the things that we learned in this video. First of all, what the definition of a coordinate system really is, what its purpose is to map out physical quantities in space. It's a framework in which we use to solve problems. And there are different kinds of coordinate systems, but they all share the same properties. They must all have an origin, a starting point. They're defined by orthogonal axes and the unit vectors that define those axes. And they all have a certain scale associated with those axes. And so you specify both the magnitude and unit in which you're defining those different coordinates. We've got several examples of coordinate systems we talked about. In the one dimension, we have the number line. In two dimensions, we have rectangular coordinates, an xy coordinate system. And we also have polar coordinates for circular or spiral motion. And then in the three-dimensional system, we've got three different coordinate systems: rectangular, spherical, and cylindrical. And again, which one you choose depends on what kind of problem you were actually trying to solve. And that's the sort of main take-home point for this video. Whatever coordinate system you use, you want to choose the one that makes it most easy to solve the problem that you're working on. And so if that means tilting your coordinate systems, or flipping between a Cartesian, or choosing a polar coordinate system instead, you choose whatever you want to use, but whatever makes it easiest to solve the problem. Now, one last point I'll point out is that when you actually start a problem, you want to stick with whatever coordinate system you start with. And so you may want to experiment a little bit with which coordinate systems are best suited for your problem. But whenever you've got one that really works, make sure you stick with it throughout the whole problem.